recorder. Okay, we are recording. Um, I just put the final exam time onto the calendar for this class. So if you have imported Canvas, schedule or calendar onto your mobile device, you should be able to see it like, soon. So this way, this is another way to help you remember that our exam is on the 18th, from 10:15 to 12:15. So it's a 2 hour duration. So do we have any questions about the final exam in terms of the time and where it's going to happen? It's going to be in the same classroom, okay? But remember, the start time of the final exam is 15 minutes before the actual lecture time. So you might want to make a note of that just so that you don't forget. The final exam is also going to be open book and open notes. You can bring the printout or handwritten notes of all the sample programs that we have talked about so far, including the homework assignment. So the structure homework assignment is due on Wednesday. The one that is due today is the recursive one. So do you want me to go over the solution of the homework assignment? Yes. So the a sample from the last semester is already available. So that is kind of representative of what the final exam will look like. I cannot say that it does not require anything prior to um, the second exam because you still need to know your flags. You still need to know what a register is, okay, because those are the basics, of the instruction set. But for the most part, it is about converting C code into assembly code. But in the process of doing that, you still need to remember certain things about what we have talked about. All right. So having said that, do you guys want me to go over the solution of the recursive or the Fibonacci homework assignment? Okay, I see one nod, two. Okay, all right, three nods. Okay, so let's go ahead and do that. All right, so let me go back to the homework assignments. And the Fibonacci homework assignment is the one that was due a few minutes ago, and we'll go over the implementation. And that's the recursive calls, code submission. And I provide the zip file. I hope everybody start with the zip file. So we'll go ahead and download this, put it onto my temp folder. There we go. All right, so I'm going to go back to the usual command line interface to actually write the code. So there we go. All right, so there are two tricky places about this particular program, and each tricky place is illustrated, or the solution of how to solve the problem is illustrated by one sample program that we have done in the past. One is the program that has Johnny, Ryan, and 12, and then the other one is the nested function call. Okay, so both of those programs are actually important to understand what to do in this particular program. So we'll go ahead and take a look at both the C code and the assembly code, but we'll focus on the actual implementation of function f. All right, so do we have any questions before we get started here? Any general problem, with this program, like, not knowing how to get started or something along that line? Okay, I don't see any questions. All right. So I'm going to start with, how to get the, how to start with a program, because there's a really kind of specific process, at least in my mind, to do it. So the first thing I would do is to look at, what the stack would look like. In other words, I look at what the frame is going to look like. The frame is determined almost entirely by, the prototype of the function. In this case, this function returns a scalar value, which is an 8-bit unsigned integer. It has one unsigned 8-bit integer as a parameter, and it has no local variables. So from that, I can determine, the offset to items, on the stack, or to be more specific, on the frame of each invocation of f. So f of n, okay, we'll start with LVS, okay, local variable size, which is 0 in this case, because we do not have any local variables. And then the way we get to the offset to the first parameter is always f LVS 1 plus. So in this case, obviously, that's a lot of extra label definition that is not particularly helpful, because we could have just said f underscore n is just 1, okay, which is fine. But I want to show you how we compute the offset to the first parameter based on the number of bytes that we need for local variables. Because once we have the more general way of looking at things, it makes it easier to implement programs or functions that are more complicated. So the typical way that I do things is to allocate for the local variables and then deallocate for the local variables. Even though there is none, you can still make the adjustment, even though it does not end up doing a single thing to the stack pointer. So we have the LDI be with f underscore LVS, subtract that much from the stack pointer, and then later on we do the reverse, which is adding that much back to the stack pointer. So after we allocate and then deallocate the local variables, the stack pointer should point back to the very last item that the caller pushes on the stack. And what would that be? What is the last item that the caller pushes on the stack? The return address, exactly. So that means at this point where the blinking cursor is, or not so much blinking, is the stack point is pointing to the return address. It is the responsibility of the callee to pop and make use of the return address. So that means I need to first retrieve it, okay? And then I have to increment D to deallocate it, because that's what a pop operation is retrieve first and then deallocate. And then I use that value to perform a JMPB back to the caller. So in between these two, okay, even though I do not really have any local variables, but I have this code to say, okay, just in case we do, I don't have to adjust the program anymore, because lines 13, 14, 18, and 19 at this point are simply saying, okay, if we have, if we had any local variables, we would have taken care of the allocation for those things already. So now we get into the actual code, and we can now take a look at the code in the C program, which is just line 5. Line 5 is using a ternary expression, which is basically a conditional statement. If n is less than 2, then we want to return just n. If n is not less than 2, then we want to return the sum of calling f with n minus 1 and calling f with n minus 2. So I'll survey the class again. Okay, do you want me to show you how to do this step by step and testing the program really step by step as well? Or do you just want me to kind of talk about the whole thing, give you the actual solution, do one test at the very end? If it works, it works. If it doesn't work, then I'll debug it at that time. So which way do you want me to do it? Do you want me to do it kind of using the very gradual way? Write a little bit of code, test it, and then go back and write some more code? Or do you want me to just kind of finish the whole thing in one shot? I can do either one. Are there any preferences? No preferences? Okay. Okay, so we can go by more gradual approach. Okay. So the first gradual approach is to implement the conditional part of the expression here. Okay, yeah, whether n is less than 2 or not. So that means I have to get to n. So this is the dependency-based kind of way of thinking, is how do I get to the value of a parameter? The way we get to the value of a parameter is to know the address first. But to get to the address, I need to know where it is in the frame. So that means I need to get to the offset first, and then we get to the address, and then we get to the value. So that's the general sequence of how we can do that. So we LDIA right now registers A, B, and C are all available. So I would use the offset first, and I get to the address, and then I get to the value. So once I have the value of parameter n, not local variable, but parameter n, I can now compare that to 2. So I would put 2 into a different register and do a CMP. But I have to be careful about the CMP is like, okay, so which way do we want to branch? So typically we want to branch to the else case, just because otherwise you would have end up with kind of additional um, unconditional branches. So that's typically how we want to set things up. So in this case, you can kind of do it either way, but if I were to do it very mechanically, I'm going to have to test for n being greater than or equal to 2, which means I'm testing for 2 being less than or equal to n, okay? So I would do the um, 2, which is register B here, and then register A over here. And then we'll do a JCI because it is an unsigned comparison to the else case. So we'll have F underscore else 0. And then also a JCI to F underscore else 0 because less than or equal to means we have to check for both less than, which is the first chance to get to else, and also equal to, which is the second chance to get to else 0. So now we specify else 0 to be here. And then because this is a if then else statement, we also know that at the end of the then branch, we have to get around the entire else branch. So we have a JMPI over here to go around the entire else branch to go to the end if of the conditional statement. And then the end if label is going to be over here to mark the end of the entire ternary expression. So right here, I can put a halt instruction here. I can also put another halt instruction over here. So I have two halt instructions. The function is definitely not done, but I can debug the program to see whether I can check whether n is less than 2 or not. So this is what I would do, is to make sure the control structure is functional first before I put anything into the branches of the conditional statement or the ternary expression. And the program is currently set up to use 3 as a parameter, which means I should end up in the else case, which means I should end up at this particular halt instruction, but not this halt instruction here. So I should end up at line 26, and then the program concludes. So save the program, and then go to the folder where I have installed River Spider. So this is using the class accessible River Spider. You guys can all access the assembler right now if you want to. And this is fib.ttp.asm. And then I just focus on the assembler right now because it's going to get a bunch of updates. When it's all done, then we can take a look at which halt instruction did we end up with. All right. So now it's all done. We ended up on line 26. So now I have to ask the question, is that the correct one? So I go back to the source code, and line 26, when you look at the blinky cursor, that in fact is the correct halt instruction. But this is not the end of the test, because I also have to test for the case when n is in fact less than 0, oh, excuse me, less than 2. So that means I have to change the function and pass it either 0 or 1 in this case. Okay, we'll just try 0 here. Save the program, and then test run it one more time. Because this time I should end up at the halt instruction that is in the then branch instead of the else branch. So we take a look at the assembler, and this time we did end up with we end up at the halt instruction on line 23, and according to the source code, line 23 is in fact the halt instruction of the then branch. So I know at this point that the conditional statement is working, and I do have access to parameter end of the function. Is that okay? So that's what I would have done first. Okay, if I were to break it down into smaller steps, I would first confirm that the ternary expression is done correctly, and then I can go ahead and implement what each part is supposed to return. So I would implement the then branch first because all it wants to do is to return n. The value of n is already in register A because I was using it for comparison. So that means there's nothing I need to do here. So I'm going to make a note here, nothing to do. because n is in register A already. But that has to do with what register I used earlier for the comparison. Okay, so if you use a different register or for whatever reason it's not in the same in register A, then you need to make sure that you copy that to register A first. What about the else case? Well, in the else case, I'm just going to change the code here and put an LDIA with some really kind of random value, like 37. Okay, just so that I know I ended up at the else case. Okay, so now we can go back, but this time it will finish the function call and it will put a value into x, which is a local variable of main. So now I have to think about, okay, where am I supposed to find local variable x of main? So that's another thing that I need to do. Okay, so I'm going to go to the share folder and create a new file or the new spreadsheet for today's class so that you guys can refer back to it if you want to, which is starting with the map of what should be where in memory. And today is 24/11, nope, 12/09. There we go. So start with a typical thing, which is basically just looking at the addresses and they are decrementing. That's my typical way of displaying memory content. And then we have decimal to hexadecimal so that we can focus on just the hexadecimal representation of the addresses because that's what the trace analyzer is going to return. And now we have to think about what should be at each location. So at this point, I have been consistently using main as a regular function. So the return address, to from main back to the entry point is going to be here. And I even know the value by heart because I can remember that it's usually 09. So that's the first location on the stack, how it's going to be used. And then main, if I switch back to the source code in C, main has a local variable x. So x is going to be consuming this particular location. X of main is supposed to be here. And depending on how I test the code, if I test the code with 03, um, then it would have a we don't know what we're going to store here. Okay, so excuse me, I cannot fill in this location yet. So what about below where x is supposed to be? So these two bytes together is the frame of main as a function, because one is the local variable, the other one is the return address. Main has no parameter, so this is the entirety of the frame from the perspective of main. So as a visual cue, I'm going to color it in a certain way. Okay, so this way we can identify this is the frame of main. And then when we call Fibonacci, okay, we have to set up a different frame. So for Fibonacci, it does have one parameter, which is n, and this is n of the function f. And if I use the value of 3 to test to test the function, then the 3 would be here. Okay, in other words, location fd should end up with the value of 3. And then we have the return address from f back to main. That should be here. That one I do not know, okay, because I need to ask the assembler where that location is supposed to be. So these two locations belong to the frame of f, okay, the function that does the Fibonacci number calculation. So we'll color code it in a different color just so that visually it is clear, which one is which one. So I'm expecting this kind of stuff on the frame. When f returns, we are going to store the return value of f back to local variable x of main. If I'm using 3, that means 37, which is in hexadecimal 25, is going to be stored here. So why is 3725 in hexadecimal? Because 37 is 2 times 16 plus 5. The 2 means how many 16s do we have in the number, and then the 5 is okay what is left after we take care of all the 16s. So that's something that I kind of expect people to be able to do. Okay, you're doing base conversion from base 10 to base 16. In the final exam, you can bring a calculator, and many calculators have hexadecimal to base 10 conversion, so you can use it if you want to. Okay, but as far as what we should have learned at this point, base conversion between 10 and 16, should be doable on the piece of paper. All right, so that's what I'm expecting on the stack, and we'll run the program, okay, and we'll see whether that is the case or not. But before we do that, I have to change main back to calling the function with a parameter of argument. Excuse me, this is a parameter of 3. So I have to change it back, and then we'll run it again. But this time the program should complete, and I should see what I'm expecting to see on the stack. All right, so it does complete, and we go back to the assembler, and then we look for updates to the stack. And all updates to RAM is on column C, so that's what we're looking at. Location FF should get a value of 09. Pretty sure that is what we think it should have, okay, like right here. So that part is confirmed. I'm gonna get rid of this one, which is from last week. There we go. All right, so the next one is going to have the 2.5 over here. Actually, I take it back. The next one we expect is the zero. No, the next one is going to be this one because we don't know. We do know that we are passing 3. So this is the next update, which is location FD should get a value of 03. So we go back to the trace. And then we just kind of scroll down and go like, okay, 03 is in fact stored to location FD. That's good. This is the return address back to main from F. So we can double check that one too. So we go to the assemble view, and then we ask when main calls F, what is the return address? So we look up, it's the JMPI to F, the location of the instruction right after that is the return address. It is to F, and then we check the analysis tab and say, oh, okay, it really is 2F here. So now we know that everything is consistent compared to what we expect to be on the stack. This turns out to be 2F in this case. When function f is done, it is supposed to return 2.5 in this case in hexadecimal because it falls onto the else case because n is not less than 2. So we now expect 2.5 to be up location fe to store a value of 2.5. So now we go back here and then we just kind of scroll down and see if that is what we eventually end up doing. Okay, that's all good. And then we'll also double check to make sure the stack pointer is balanced, which means it goes back to 0, 0 by the time we get to the only halt instruction left in the entire program. So this is how I can tell that the program is working up to this point, which means the then branch is probably working. I don't know yet. I haven't tested it yet. But the else branch seems to be getting the control correctly. It's returning the correct value. Main is doing everything correctly. It is storing the return value to local variable x. So that's my confirmation of a few parts of this program. So after that part is done, I can now focus on getting F completed because I know that the conditional branch is working. We also know that main is doing what it is supposed to do. So what is left to do is to replace this part with the actual recursive call. So this is going to be kind of the last stage, but I can break this up into multiple stages too. So right now at this point, okay, at where the blinky cursor is, um, parameter n is still in register A, okay, because by the time we end up here, it is right after the CMP on line 20, which means register A still has the value of parameter n. In the final exam, one thing that might be very helpful is for you guys to really comment every single line so that you know at all times which register has what in it. Okay, because otherwise you get to a certain line and it says, okay, why are we doing this to register A? Well, that's because register A has the value of n. Because I'm just going to do a decrement A because that becomes n minus 1. Then I have to push it on the stack, std a. Okay, so now I have just pushed f of n minus 1 on the stack. And now I can just complete the rest of the function call, which is getting the return address, okay, dot 6 plus, decrement d, stda, and then I can do a JMPI to the function that we're supposed to be calling, which turns out to be the function that I'm in right now. Okay, but that doesn't really change the sequence of how we call a function. All the conventions of calling a function still applies in this case. When a function comes back to this location, the first thing I need to do is an increment d so that I can deallocate the argument that is still sitting on the stack, and now I should have the return value in register A. So we'll go ahead and just do this much. In other words, I'm changing the function here. Okay, so if I were to kind of comment this out and say, okay, what are we testing or how we are testing the code? We're basically turning the double recursion into a single recursion. And if you turn it into a single recursion, then all the f value of n will either return 0 or 1. Okay, if you ask originally what is f of 0, it will return 0. If you ask for anything other than 0, it will return a 1. Okay, so that's what we're expecting this program to do, which means we are expecting local variable x of main to be 1 once this program runs. Okay, there will be recursion. There will be a big mess of putting additional stuff on the stack, but eventually I'm going to store 1 as a value into local variable x of main. Now, debugging this code is a little bit easier because it doesn't have double recursion. Without double recursion, it kind of means that you can look at the remnants on the stack and try to figure out if things went wrong. You can look at what is left on the stack to figure out what went wrong when the program ran. So I'm gonna save the code. Oh, okay, I need to save the one in assembly first, and then we'll give it a try. So we are expecting 1 to be stored this time at location FE eventually, and the stack will be a little bit more involved, because of the recursive call. So we'll take a look. Okay, so we go back to the assembler, and then we have to scroll down quite a bit, but we are confirming that 1 is stored back into location X of main. So that means the single point recursion is working. Okay. So once you know a single point recursion is working, then you can work on the double recursion. The trick of doing the double recursion is right now at this point, register A has the value of f of n minus 1. And where am I going to stash it when I need to call f again with the argument of n minus 2? So that really is the big question, is where do I stash it? I can put it into register B or C because they seem to be available right now. But according to the caller-callee agreement, your callee, the function that you're calling, can trash all registers except for the stack pointer. So I cannot do that. I cannot just say, oh, we're going to save, excuse me, register A in a different register. The only safe place to stash it this time is on the stack. You have to push it on the stack. And that trick is illustrated twice. Once by a sample program that calls your 5FIVE as a function, twice as one of the labs that you have done. Okay, it's actually embedded into the lab itself. And then the second time we talk about this technique is when we talked about the sample program that has Johnny 5, okay, and Ryan, which is returning a 7. And then we are trying to add the return value of both function calls. So that's how this technique was, this technique was demonstrated. So but now we have to push it on the stack, which means we have the decrement D and then STDA. So you might say, okay, but doesn't line 33 and line 35 cancel out each other? The answer is yes, they do cancel out each other. If you comment out both lines, the program will work just the same. In other words, we can simply overwrite that 1 byte that was used to store an argument to store the return value. We're just overwriting it, okay? It just ends up doing exactly the same thing. But from the conceptual perspective, they are two separate operations. One is to deallocate the argument from the stack, and then the other one is to push the return value on the stack. So conceptually, they are two different operations, but they just turn out to have instructions that cancel out each other. All right, so now that we have the return value of f of n minus 1 pushed on the stack, we can try to call f of n minus 2. But at this point, I don't even know where I can get n, so I have to recompute n from the call frame. So that involves LDI um, register. Okay, it doesn't matter which register because I already saved register A, so it's loading the offset of n into a register, add that register to the stack pointer. But the problem with this approach is we have already pushed the saved value or the saved return value of f of n minus 1, which means the stack pointer is not pointing at the base of the frame anymore. It is now pointing to 1 byte below the actual base of the call frame, which also means the offset of 1, which is where I'm supposed to find f of n from the base of the call frame, that number has not changed. But the stack pointer is not pointing at the base of the frame anymore. It is now pointing at 1 byte below where the base is. So that means all the calculations require to account for that one additional byte. This is the easiest way to do it. But if you want to do it the other way, which is doing it this way, it works too. Okay, it's just the second method, which is what you're seeing on the screen right now, is not as efficient, but it will get the job done too. And if you do not remember to do this step, your program will not work, okay? It will not work as expected, but then you can debug it. So do you guys, so once again, we can potentially have a fork here, which means, do you want me to intentionally make the program not work and then use the trace to debug it? Or do you want me to just to get it right the first time so that you can actually just see the solution and be done with it? Option A or option B? Feels like going to the optometrist. A or B, one or two. Option one, which is to intentionally make the mistake and then see from the trace how we can fix it. Correct? Okay. So let's do that. Okay. So we'll go ahead and take out, the adjustment, and then we are going to load AA because otherwise we have the quote unquote the address of n. We need to get the value of n, and then decrement it twice because this time we're supposed to push n minus 2 on the stack. So we have to decrement A twice, then we push it on the stack. So that's how we push something on the stack. And then we push the return address on the stack. Okay, LDIA dot 6 plus. Oh, LDI. There we go. That's why I like syntax highlighting. Decrement D, stda. So now we have both the argument and also the return address pushed on the stack. I can now continue execution at the function that I'm calling. When it comes back, deallocate the argument. So at this point, supposedly, we have the return value of f of n minus 2 in register A, and then the return value of f of n minus 1 sitting on the stack. So we have to pop that from the stack first. Okay, so we do a LD BD increment D. So we are popping the return value of f of n minus 1 from the stack. And now we can just add AB because we're adding the return value of f of n minus 1 and the return value of f of n minus 2. The sum of those two become the actual return value, and this should get the whole thing done. But we already know that we still have a bug. But I want to show you what the bug is going to show, how it's going to show up. And this one is actually not too nasty to find. Okay, so I'll show you guys why I say so. It's taking a long time for the assembler to come back. This is on the cloud side. There's not much I can do about this. Okay, let's check out the source tab. Is it getting updated? Yep, it is getting updated, just taking its time. All right, there we go. All right. So what we need to do this time is to figure out, what is the stack going to look like? So we have three, okay, and then three is going to call two, which is going to call one, and then it returns. Okay, so I'll step by step go through, what the single point, what the double point recursion is going to look like. So the next two, okay, is going to be f. In order to find what is f of 3, it's going to have to go find f of 2. So that means, these two, okay, I'm just going to repeat it here. It's going to do a recursive call with f of n minus 1, which is f of 2, which in return will try to find out what is f of 1. Okay, so I have to do one more time before the recursion ends. So at this point, there would be 3 frames on the stack. I'm just going to change the color to kind of make it clear that we have basically 3 frames of f on the stack right now. And this is going to be f of 1. F of 1 does not do recursion, right? Because it is less than 2. So that one is going to return right away. Okay, so that means at some point these two they're not exactly gone. It's just that they are not on the stack anymore. The stack pointer is going to be pointing back to this return address. Okay, and at that point we are going to save the return value of f of 1, which is just 1, which is going to be on the stack. So that means this location is going to be f of n minus 1 that is being pushed on the stack, and that is just 1. Okay, so I'm going to have to get rid of the strike out or the strike through. And then it will push n minus 2 on the stack, which is a 0. So this location is supposed to be n of f, which is in this case that is supposed to be 0, 0. Okay, I have to get rid of the strike through too. And this is where the problem is, because I knew this would be a problem, but I did not fix the problem. It would have pushed the wrong value here the second time I update f8, which is the point of the second recursion. Okay. Um, so how do we know that it is not doing this right? So you have to go back to the analysis tab, and you have to look for exactly that point of time. But since we are assuming that we don't know there's a problem, so we have to go like, okay, what can I expect to happen, in this particular instance? So by the time we okay, you're supposed to track everything, okay, all the way back to the recursion that comes back, and then it will push the second it will push n minus 1 on the stack. Okay, the first time you push n minus 1, n minus 2 on the stack, it will push the wrong value. So in the C code or in the assembly code corresponding to that C code, we are referring to this instruction here on line 43. That's going to push the wrong value. So you have to basically check and track the entire program's execution up to this point and go like, why is it pushing not a 0 on the stack? Okay, so we can now go back to the trace. I know this is cheating a little bit because I know exactly where to look, but if you make that mistake, to begin with, you probably would not know where to look. But that would be the first point of deviation from what you expect. So that would be a line 45. This one here, line 46. So you can see how it is pushing. Oh, this is the return address. This is the actual. Is it line 43? Yep, it is line 43. Okay. So this is the time. This is supposed to be a 0. This f, they're storing a 2 1 to f8, is supposed to be storing a 0 0 to f8, and the prediction is correct too. This is the location where we are supposed to push n minus 2 on the stack, which is supposed to be 0 0 at that point, but instead of pushing a 0 0, it is pushing a 2 1 on the stack. So that's when you notice that, oh, okay, something is not right. Why is it pushing a 2 1 instead of a 0 0? So you have to execute a program backward in that case, which is basically saying, okay, we know register A has 2, 3 in it, and we decrement it twice. So the 2, 3 is wrong to begin with because it's supposed to be 2. Okay, so now you have to ask, why are we putting a 2, 3 into register A on this line? Okay, LDAA. So with LDAA, you are assuming that before the LDAA, register A has the address of N. And in this case, that's supposed to be FA, and that's supposed to be the address of A. But when you look at the frame, okay, when we do this by hand, you can see that FA is not N of F. Instead, it is the return address, because at that point we would have pushed this already, and the stack pointer, which is usually pointing at the base of the frame, is not the case anymore. Instead, it is now is pointing to the last item that we just push on the stack. So that is why the calculation was wrong. But you have to pay close attention to what address did you use to dereference to try to get the value of N into register A. And because it's getting the wrong value, it's getting the wrong value because it's using the wrong address. The address is wrong because it is not taking into consideration that the stack pointer is now pointing to 1 byte below where the frame is supposed to be starting at. And we forgot about that 1 byte. Is that okay? Does that kind of help explain the process of how to debug a program? So yes, you have to mentally track how the stack is supposed to be used in order to find the bug to begin with. Because without knowing what I'm showing here on the in the spreadsheet, there's no way to actually find out that your program has deviated from what it is supposed to do. Are we still doing okay so far? All right. But the process of debugging a program is actually a very productive use of your time, even though you may not feel the same way, because that's how you really kind of exercise all the things that you have learned up to this point. Because to construct this particular map here, to figure out how the stack is supposed to be grow, retract, and then grow again, and this is supposed to be what you're supposed to be seeing, that is really, really the best way to study for this class is to exercise all of these things and then figure out that, oh, we are supposed to push a 0 here, but we are not pushing a 0. What is happening? And then you go back and figure out that, oh, okay, I got the address of N wrong because I forgot that the stack pointer is not pointing to the base of a frame anymore because I just pushed the return value of f of N minus 1 on the stack. So to fix the problem, okay, once you figure out what happened, then to fix the problem, as I mentioned a little bit earlier, you can do a 1 plus over here, or you can do a increment a after the add AD or before the add AD. It doesn't really matter because eventually they all got added together. So there are a few ways to fix the problem. This is the most efficient way to fix it, but there are less efficient way to accomplish the same thing. All right, so I think I fixed the problem, which doesn't mean that I actually fixed the problem, right? So I need to kind of save the code and then run it again just to make sure that I did have the problem fixed. So I have to run it one more time. And I'm letting the assembler to stay at exactly that spot so that I can check exactly that spot before proceeding any further. So now I can see that I push a 0, 0 here, right here. So I got the problem fixed because this is as expected. I'm supposed to push n minus 2. Since n is 2, n minus 2 is a 0. That's what I'm supposed to push. So I know for sure that I have fixed that particular bug. Now, whether the program has some additional bug, let's check. So f of 3 is supposed to be, so the question is f of 3 2? So f of 3 is f of 2 plus f of 1. F of 1 is just 1. F of 2 is f of 1 plus f of 0, which is just f of 1, which is also 1. So we end up with 1 plus 1, which is exactly what we see here, which is 2. So f of 3 is supposed to return a value of 2, and that's what we are storing into local variable x of main. So the program did correctly, did the calculations correctly. All right. So that's kind of my demonstration of the Fibonacci program. Some of what I just mentioned is going to be a technique that can be helpful for you to finish your traverse program. Okay, even though the traverse program is a little bit more complicated, it has double pointer and stuff like that. the process to debug it is kind of the same way. Okay, you just start with not so ambitious your programs, right? You start with a program that is not ambitious. You just want to get one thing done, and you want to verify that you got it done first. So at this point, I want to see how you guys want to proceed. Okay, do you have any specific question you would like to ask about assembly language implementation of a C function? And this time it can be specific to the traverse program. So are there any specific concept of the traverse program that you would like to ask? So we'll start with conceptual stuff first, and then we can move on to actual implementation or kind of more procedural stuff. No questions? Okay. Well, I cannot give you the solution of that homework assignment just yet. So what I can do is to use the remaining portion of this time to talk about the final exam. Okay, because I think that actually may be helpful for the homework assignment as well. So that's what I'll do, unless somebody has some specific question, then I can address those questions too. All right, so let's take a look at the final exam from spring 2024, which is a format I have been using for a few years. Okay. But each year has a different program. So, you're more than welcome to dig up all the programs from the past years, okay, because they are all a little bit different. All right. So the format is you are starting out with a C program, which is usually on the last page. And I am giving you all of these pages with usually just a paper clip, which means you can separate the last page so that you can always reference the C code. So this particular C program looks kind of complicated because it really is complicated. I was planning to do something even more complicated, and then I figured that I ran out of RAM space. I couldn't really assemble the program. So this is just the portion that I could fit in the processor. All right, so the concept is not for you to really understand what this is supposed to do, but to understand how to implement each individual statement in assembly code. Okay, so I want to kind of make sure that you understand that is the focus. So the focus is not to understand data structure or to understand all of these kind of complicated code. The whole idea is, given this is the code, do you know what the assembly code is supposed to look like? That really is the bottom line of the final exam. So you look at each concept and then you have to ask, do I know how to do that? This is a structure definition. We have talked about structure definitions in C from translating that from C to assembly code. So that should not be a big problem. It is returning a pointer, but a pointer is just a scalar, which means it goes into register A. That should not be a problem. Pos is a um, pointer to a structure, which means it is really just an address of some kind, takes up 1 byte on the stack. It's just that where it points to is the first byte of a structure. So conceptually speaking, should not be a big deal. Remaining itself is just an unsigned A-bit integer. It is by itself an unsigned A-bit integer, so that's not new either. So the first thing that might look a little foreign to you is n is a local variable, but it is a structure. So now we have to think about what do we do when we have a local variable that is a structure? Does it change anything that we have talked about? The answer is no. It is not supposed to change anything that we have already talked about. So when we get to the assembly code, I'll illustrate what I mean by that. This one does have multiple points of return, which is kind of icky, but the other way is even more clumsy. So I kind of chose to have multiple points of return. Um, so the really kind of more tricky part, maybe this portion here, okay? Because we are comparing um, what is pointed to by a member that is in a structure that is in return pointed to by a parameter. So that may be a little bit tricky on the tricky side. And then I mean, this stuff here should not be particularly tricky. We are passing the address of a local variable, which is a structure, as a parameter. So that may seem tricky, but it really is not, that tricky. And then when we look at main, we have a few lines of initialization. A is an array that is also a local variable. The size of the array is 3. First is also a local variable, but it is of a structure type, and so on. Okay, so this is the C code. And now we have to go back to the assembly code implementation and check whether the whole program is done correctly or not. All right. So instead of focusing on all the details, okay, because the actual code starts about here, what I want you guys to at least think about or consider is can you develop a bunch of checklists and say, okay, if I'm looking at a conditional statement, this is the checklist. All these items should be somewhere that I can find in a particular order. If I'm looking at a function definition, I have a different checklist. These are the things that I should be expecting. If I'm looking at a function call from the caller's perspective, I have another checklist to say, okay, these are the things that should happen, and I would just have to check off each item. Okay, so now the question is, can you come up with a checklist like that? The two source documents for that, for you to basically develop your checklist, would be the module that talks about compiling, okay, because that one talks about how to convert from a conditional statement in C into the structure in assembly code. And then the other one is going to be the caller callee agreement, which is describing a bunch of stuff, okay, from the caller's perspective. These things are your responsibility. You better do it. And then these things are on the callee side. You better do these things, okay? So so having a checklist is helpful because I can forget about certain things myself, okay? Just because I'm forgetful. But having a checklist means, oh, okay, I have something to follow. There's a structure that you wrote, okay, with little check boxes for you to fill in. But the key is bring multiple templates with you because there will be multiple function calls. There may be multiple functions being implemented, and so on and so forth. Okay, so you kind of have to make sure that you have multiple checklists so you can use one for each instance of calling a function or implementation of a function or conditional statement or loop and stuff like that. All right, so we'll start with this program. I would try my best to interleave the C code within the assembly code so that you know where the C code is supposed to be or what the assembly code is supposed to be doing, within the context of the C code. The entry code is not, in the C code, so that's why it is not even, in the C code itself. So in this case, the only change is instead of doing an LDI D0, I use a shortcut to um, make sure that D starts with a value of 0. Sub DD would do that because subtracting register D from register D will end up with register D being 0 because D equals to D minus D. Is that okay? Does everybody understand why sub DD is really kind of like a shortcut to do a LDI D0? Okay. Then we have decrement D, LDI A dot 5 plus, and so on. So now some people may be asking, but that's wrong. Well, it is not necessarily wrong. It is different, okay? Because most people remember dot 6 plus, but this is a dot 5 plus. It must be wrong. So this is where I would recommend a different way to study or different way of understanding the material. Instead of remembering a sequence, which is, oh, we always do it like dot 6 plus, and then we decrement D, and then we do a L, uh, STDA, and so on, and then the JMPI, instead of remembering just a sequence without questioning why the sequence works, question why the sequence works. Okay, it is the mechanism that is important. In this case, the only is LDIA dot 5 plus is not the only change because the other change is this time I also performed the decrement D first, which means the number of bytes between the location of the opcode of the LDI and the location where the halt instruction is actually 5 this time because decrement D is done before the LDI instruction. So the same principle still works. There's nothing wrong with this code. and marking code that is actually right wrong, okay, or attempting to fix code that is already working correctly will get points deducted, okay? Because I want to make sure that you guys understand why this works and not just that, oh, this is the pattern. I recognize the pattern, or I recognize the pattern is different and therefore it must be wrong. Nope. I'll be testing whether you actually understand why a particular pattern works. All right? Yes. So the decrement D needs to happen because in the push, you need to decrement the stack pointer. Now, the only way for me to have, like not even having the decrement D is to do a LDID FF or 255. In other words, I pre-decrement the stack pointer instead of having it initialized to 0. I have it initialized to 255. Then I don't need the decrement D. But that's really really bad practice because it means in this special case I'm not following the same um, principle of using the stack, which is when you push, you always decrement the stack pointer first, and then you store to where the stack pointer points to. So I would not do something like that. That's I'm religious about that sort of thing. All right. So there's nothing wrong with this code, JMPI to main. Okay, it's all good. So you might want to also have a way to kind of help you remember which part of the program is already checked. Okay, you can just kind of use your own little notation, okay, to kind of remember which part of the program you have checked already. So the next thing we do is we look at the offsets of members of the structure R, okay. PN is the first member. It is at an offset of 0 from the beginning of the structure. PV is the next one, and it starts with the offset of the first member and then plus the size of the first member. It is a pointer to a struct R. Any pointer has only 1 byte, so that is correct. The size is the offset to the last member, which is PV, plus the size of the last member. That is a pointer to a signed A-bit integer, so that is correct as well. All right, so now we go to flip run, and flip run has 2 arguments, and let me see, does it have local variables? I think it does. It has n as a local variable. That's it. Okay. So now we look at the function definition, and then we try to work out what the frame is going to look like. It has a local variable, and it's the only local variable, and it's the only local variable in this case. So the offset from the frame to the local variable is going to be 0, okay, because that's the only thing you have. That's the only local variable that you have. But the size or the number of bytes I have to allocate for the local variables, this is actually correct because it's not 1 plus, it is R underscore size plus because that one single local variable is a structure. So you have to make sure that you allocate enough bytes for the entire structure. So now the question is, did I just change something that we have been doing all along, like the 1 plus? Well, the answer is yes and no. Okay, I changed the 1 plus to R underscores size plus, but I haven't really changed the concept because you still have to allocate enough bytes for all your local variables. It just turns out that this one single local variable is not using a single byte. It is a structure. It uses up, in this case, 2 bytes. So you have to allocate 2 bytes for the local variable. So there's nothing wrong here. So LVS is done correctly, and then PPOS is the first parameter, and it is defined to be LVS 1 plus. This 1 plus, this one here, has to do with the return address, because the return address is below all the parameters, but it is above all the local variables. So this 1 plus is for me to skip over the return address. And then remaining is my second parameter. Its offset is the first parameter, which is ppos, plus the size of ppos itself. This one is also correct, even though ppos is a pointer to a struct R, but since it is just a pointer, all pointers only take up 1 byte in the architecture. So these offsets are all correct. So the next few items I would check is I look at the entry point of the function. I make sure that I'm allocating for my local variable, and then I immediately skip around all the way to the end of the whole function and go like, did I deallocate those things before I return? So this is the code to do the deallocation. So that is correct. But since I'm here already, I also want to double check, did I also, do the return code correctly? This time I did not, because the um, LDBD is going to retrieve the return address from the stack. Increment D deallocates that location. What is, am I missing something here? I'm missing the jump. Exactly. Okay, so that's the sort of thing that you have to watch out for. Okay. Um, but this is also the kind of thing where a checklist can be very helpful. Okay, because all you have to do is to go like, okay, from the implementation of a function perspective, what needs to happen. Okay, if it has local variables, you better make sure that we allocate and deallocate. But every function has to return to the caller. So how do we return to the caller? All right, so I would identify there's a problem here. We need a JMPI, right after the increment D. Then I would go back to the actual body of the function. In other words, the way I would do the checking is not linear. It is not just sequential. I would go structure by structure. Okay, I look at things from the structure perspective. All right, so now the C code says, I need to see if remaining is 0 or not. If remaining is 0, we'll do the then branch. If it is not 0, then we'll go to the else branch. Okay, in other words, we're dealing with a conditional statement. So now you have to ask, okay, if we're dealing with a conditional statement, what things should be there? The C code demonstrates pretty clearly we're looking at if, then, else. In other words, this is a full conditional statement. So with a full conditional statement, you should have a then branch. Where is the then branch? I think this is the then branch. You can also double check and verify that this is what we're supposed to do, for the then portion. And then the else portion is right here. But you also need to make sure that there's an unconditional branch around the else branch to go to the end of the entire conditional statement. So you have to make sure that that is there, okay? And then the else branch is here. We also have to make sure this particular label does exist and it is at the right place. So you have to kind of scroll down, look at the where flip run underscore ret return is defined, and it's all the way down here. And you can look at the nesting of the braces to make sure that you're at the right place too. So I'm commenting even the closed braces just so that you can understand the structure of the code and where the assembly code is supposed to be corresponding in the C code. So that should come in handy. So I have just double checked that the conditional statement is implemented correctly. It has all the proper elements. So now I need to check, okay, so if I need to see if remaining is 0 or not, okay, how am I going to do that? This is the offset, this is the address, and then I immediately go for AND CC. In other words, I'm doing something with the address of remaining and not the value of remaining. In the C code, am I doing something with the address of remaining? No, I'm doing something with the value of remaining. But the assembly code is doing something with the address of remaining, which means I think we need a dereference, right? So I would need to insert a line between 95 and 94 and 95 that is LDCC. Okay, because otherwise I'll be using the address of remaining and see whether it is 0 or not. It's always going to be non-zero in that case. Okay, it doesn't make sense. So I need to insert one line of code between 94 and 95. It is going to dereference C. But to get full credit in the final exam, you also have to kind of explain to me why you need that instruction. Okay, so it's not just a pattern recognition kind of thing. It's like, why do you think we need this instruction here? All right. So once we have the additional instruction, we'll be taking the value of remaining and then do an NCC. So now you have to remember what it does. Okay, it forces the value of remaining through the ALU, and therefore it will influence at least a few flags. The Z flag is one, the S flag is the other one. The Z flag is the only one that I care about because the original expression in C is just checking whether it's a 0 or not. With TTP, the only way you can do is to do a conditional branch if and only if the Z flag is set. So now we have to say, okay, what if the Z flag is set? If the Z flag is set, it means remaining is 0. I think we're supposed to go to the else branch in that case. Actually, I take it back. I take it back because if not remaining means, if remaining is a 0, I go to the then branch. So this is correct. It is going to the then branch here with the JZI. That is correct. But the next one, which is what if it is non-zero? What if remaining is non-zero? I think we're supposed to go to the else branch. So that means the label of the next line, this portion here, is supposed to correspond to the label of the else case and not the then case. So you will need to fix that one. Okay, and just give me a kind of brief summary of why you think that it needs to be fixed. But it needs to be fixed here. All right, so now we can move on to the actual then branch, which is supposed to return the value of the member PV of the structure that is pointed to by PPOS, which means I need to get to the value of PPOS first. This is the offset, this is the address, this is PPOS itself. This is the offset from the beginning of the structure to the member PV, okay? And then add the two together, and then C would end up to be the address of the member PV of the structure that PPOS is pointing to. And you may see something like this as well in your test, which is asking you to explain what is in a particular register. In this case, the destination register is register A because that's the one getting changed. So what you need to do is to explain to me what is in register A when this is all done. So you can use a C expression. The easiest way to solve this problem is to use a C expression, which you can just kind of put it here. Okay, you can just kind of specify that register A ends up having this particular expression in it. Okay, that would be the easiest way to do it. But if you want to spell it out in English, like what I just did, that's fine too. Are we good so far? Okay. But I can also potentially ask you what is in register C instead of register A. Then you will have to tell me that it is the address of the member PV of the structure that is in return pointed to by PPOS. Okay, so you have to pay attention to what I'm asking you. And we already checked the JMPI to the return label, okay, because that exits the entire conditional statement. So we got that checked already. All right, so now we move to the else case. The else itself, the else case of the top level conditional statement has a nested conditional statement. So this is basically the nested conditional statement inside. The first thing, it has an or, and it wants to say if remaining is 1, then we go to the then case of the nested conditional statement. Or if this statement is true, we also want to go to the then of the nested conditional statement. So now you have to kind of track all that stuff and ask, what are we comparing here? Okay, I know what B is because B is just loaded with a value of A. But at this point, what is in register C? Okay, so how do we answer a question like that? What is in register C on line 112? Because it doesn't seem like I put anything into register C recently. So now you have to backtrack a little bit and ask, how can I end up at label else 0? Okay, I can end up at else 0 only because of a JMPI to else 0, which means you will have to fix this bug earlier first, because otherwise there's no branch to else 0. Okay, the code starting at else 0 cannot possibly execute without without a branch to it. So now you have to ask, okay, so I can go to L0 only because of this line, because this is supposed to be L0 and not then 0. So now you have to ask, what is in register C, at this point? It is supposed to be remaining. In other words, register C is supposed to have the value of remaining by the time we get here. So comparing the value of remaining to 1, seems to be the right thing to do. Ordering does not matter in this case because I'm looking for a equality. This is not an inequality, so which way you want to compare doesn't really matter. Okay, so that's okay. I got this cleared. But this is also important. It also illustrates the importance of tracking which register has what value when you are you know, analyzing the program. So now we have a JCI to the then branch of the nested conditional statement. The label itself, the naming of the label itself, is also supposed to help you a little bit because the reason why this label that is highlighted is called else 0 underscore then 0. The zeros are referencing the relative position of the conditional statement. Okay, in other words, the L0, the 0 of L0 means this belongs somewhere inside the else branch of the first conditional statement at the top level of the function. Now, you guys may say, but there's only one in the top level. Yes, okay, but it doesn't mean that the next program only has one. So I just make sure that I can designate which conditional statement at the outermost level of the function I'm referencing. But this is not just referencing that we are inside the first conditional statement. We also know that we are in the else branch of the top level conditional statement. Okay, so now you look at the else branch of the top level conditional statement, which contains its own conditional statement. So the second part, which is the then 0 here, is referencing we are now in the then branch of the nested conditional statement, which is a part of the else of the top level conditional statement. In other words, I'm trying my best to use the name of the label to tell you what this is supposed to be corresponding to in the C code. Okay, so try to make use of that. So the question now is, am I supposed to go to the then branch if remaining and one are the same? The answer is, yeah, I think that's what we're supposed to do. So this is fine. Okay, so you can just kind of mark this as okay. And then, so that takes care of this one, which means if this is not equal to, if remaining does not equal to one, we better check the second part of the or, okay, which is what the other part is talking about. It might be helpful to you to also, add additional comment. You can add additional comment that does not constitute an answer to the answer. Okay, I don't mind. So you can mark it up and go like, oh, okay. So now this block of code down here is referring to the second part of the or. This is the right hand side of the or. This is the beginning of the second part of the or. All right, so let me scroll down here a little bit. So now we track each line of code. B has the offset, and then the address of PPOS, and then B eventually has PPOS in it. Okay, that looks kind of the right thing to do. Okay, because both this part here and this part here seems to require PPOS to be uh, in the register first. So that takes care of all the way to line 116. Seems to be doing the right thing. And then line 117 is giving us the offset to member PV of a structure of type R, the struct R, and we add these two together, which means we are now getting to the address of member PV of the structure that PPOS is pointing to. In other words, we are looking at the address of this expression here. But obviously, we are not interested in just the address. We're interested in the value of that member. So that means we need one dereference here. So after line 119, register A is the actual expression that I have highlighted here. So I load that into register A. I load it into register C. So I load it into two separate registers. And then I increment A. And then I load A, indirect A. Okay. So now the question is, what am I doing? Okay, so I'm taking this, okay, register A at this point of line 119 has the value of PV. So that means on line 120, which relies on the result after A is dereferenced is going to have the asterisk of this entire thing. I have just dereferenced the entire thing. So that means register C of line 120 actually has the value of this entire expression. Is that okay? And then I increment A. Okay, so A still has just P pos points to PV. And then I increment A, which means now I end up with this expression here. And I need to dereference it one more time. Then I have both this side and this side. The question is which register has which side? Register A has this side here. Register C has this side over here. Okay, and then I compare those two, and I say if A is less than C, we'll go to the then zero case. Okay, so let's check whether that is correct. Okay, this is in register A. This is in register C. If register A is less than register C, then this entire expression is true. When that expression is true, the OR is also true. And because this is the condition of the conditional statement, so if that is true, going to the then case of the conditional statement is the right thing to do. So I can now check off that portion. The JLI also needs to be checked because there's JLI and versus JCI. You have to choose the right one. JCI is good for unsigned comparison. JLI is good for signed comparison. In this case, you have to look at the member PV. Does it point to a signed integer or does it point to an unsigned integer? I believe it points to a signed integer. Let me double check. So we kind of have to go back to the C code here. So it is a signed integer, okay, right here. So that means on line 116-ish, it is doing the correct thing, okay? And if it is not less than, then if we fail both of these conditions, then I go to the else branch of the conditional statement that is nested in the else branch of the outermost conditional statement. That's what it's saying here. So once again, I forgot to do one thing. Okay, I forgot to double check um, the structure of the nested conditional statement. So the then case is supposed to have a unconditional branch around the else case. That is actually here. That's good. And then this is the actual else case of the nested conditional statement. All right. We are almost running out of time. It seems like, this is as far as I can get in today's class. Do we have any questions about the approach? When you listen to me explaining it, there's a lot of words, okay? When you So one thing you can do, okay, depending on how much time you have, and depending on your progress of the Traverse program, is really kind of do the same thing that I just did. Okay, try to comment in your own words what is in each register as you go through this code. And in the process, okay, you can also listen back to what I did in today's class, and then you can try to develop your own checklist. Because I think if you have a checklist of everything that is supposed to have a template, that will really help you remind you what to check so that you're not going to forget about, oh, I know this is supposed to happen, but I forgot about it. Okay? If you have a checklist, you're not going to forget it because the checklist will remind you what to check. So that's why it is important to develop that checklist. But the answer, but I'm not going to give you the checklist, okay? Because I think this is something that you should develop because once you understand the concepts, you know, it's just mechanical to come up with that checklist and make use of the checklist. All right. So we are out of time in terms of the lecture. I will stop right here on line 132. Okay. So when we come back on Wednesday, we'll talk about both the Traverse program and also resume our discussion from line 135 of this code. All right. So we'll start the lab time. There's no structured activity for the lab time anymore. So this is more or less a time for you to work on the program if you want to do it during the lab, Or if you have any questions about your lab, or the program that you have been implementing and you want me to take a look at it, or if you want me to help you set up Reefer Spider, that's how we're going to use the lab time, for today. And also for Wednesday, there's nothing else to do because we would have the program already due at that time. So the lab time of Wednesday is kind of like just kind of an extension of my office hour. If you guys have any questions about the content of this class, I can answer those questions at that point. All right. So do we have any additional questions? Yes, the recursive code. Yeah, I can send it to you. I mean, I can just zip it up and then send it as an attachment. Yep. Let me let me do it right away before I forget. Yep, absolutely. So there we go. Zip. Yep. fib.c, fib.ttpasm, and it will just appear as one of the announcements. Can you guys sign up for classes next semester right now? I guess some people can, some people. Okay. Okay, just a reminder, okay, this has nothing to do with assembly language programming. Make sure that you budget your time. In other words, plan ahead of time for each hour of lecture. Plan to use 2 additional hours to review the notes and whatnot, because the number one reason people are not doing well in the class, okay, that's because of me, the instructor. But the second most common reason is they ran out of time because there's just not enough time budgeted for all the classes people are taking. So take that into consideration, especially if you work your part-time or full-time, that becomes even more of a concern. So there we go. All right, so I will give you the Fibonacci solution. Okay, solution of the recursive program. And because of the open book and open notes nature, if any program, any solution, you think, oh, this is going to be useful because it illustrates a really kind of tricky thing, you can always print it out and bring it with you. There's no limitation of how much material you can bring as long as it is on paper. But you need to somehow index those items too, especially if you bring in a big pile of paper. So that way it's easier for you to locate the correct one. So that's all. Okay, so I'm gonna send this to you, but otherwise the lecture is done. And if you want to stay for the lab and you have questions to ask, I'll be here. All right. So yeah. Mm-hmm. Oh, what mistake did you make? Hmm. Okay. It's AuyeUnt, not IEUNT. So it's okay. You got two mistakes. You can always just forward the one that was sent to the wrong address, that bounced back to you, so you can forward that one to me. I think the attachment is still in the forward. So this way it has a little chain and I can see that, okay, you sent this originally on this date at this time and it's just a wrong address and you're just resending it. Yeah, it's AUYEUNT at arc.rolesrios.edu. Yep. Mm-hmm. All right. 423. I would probably not have enough time to talk about it. Practice. I can do that. You can probably look up my lectures from last semester because that's typically what I do is I just use the exam from the previous semester. Okay, sure. So this is the exam, final exam from fall 2023. You can look at the lectures from 2023, up from spring 2024 for the solution to this exam and attach. All right, there we go. Mm-hmm. Yep. Mm-hmm. Okay, so mm-hmm. Yeah, yeah. I understand. I understand you want to get the reassurance, right? I understand that, but I'm smiling a little bit because it depends on 37.5% of which portion, right? So if you're getting 37.5% of everything that is already graded, and you are projecting that you will get the same score for your submission for the homework assignment, that is usually not very significant, but just in case you're right at that border, so you kind of have to take that for okay. So then the answer is yes, because the way I do it is I just add up all the points from the different sources, and then when I add everything, if you have more than 37 point, if you have at least 37.5%, then you're passing with a C already, at least. Yep. So I think what you said is correct, if I understand it correctly. Yeah, yeah, yeah. It makes sense. It makes sense, because you might need to prioritize your time to something where you may not be guaranteeing a passing grade yet. So I understand that. Not a problem. Mm-hmm. Mm-hmm. Yep. The traverse one? It is not a practice. It is your homework assignment. Okay, that is in Canvas. It is okay. So you probably have not clicked on it yet. This is your homework assignment. It is due on December 11th. Yeah, yeah. So you might need to click on it because it does have a link to a file where you need to download, and there's a video to kind of show you how to approach this particular program. Yep. Yep. Okay. Mm-hmm. Yep. You too.